Hello everyone and welcome back to Differential Equations. The last time we were discussing complementary solutions, and to get a complementary equation we took a linear differential equation with constant coefficients and we set the right hand side of the equation equal to 0. And then we rewrote the equation using operator notation. And then we factored y out of the left-hand side. And that gave us a polynomial in terms of the operator d. We called the polynomial phi. And from that form of the complementary equation, we took the polynomial phi and evaluated it at the variable m and set phi of m equal to 0. And that was our auxiliary equation. The roots of the auxiliary equation pretty much give us the solution to the complementary equation. Now, things don't always work out that easily. Last time, we said that if we have a linear differential equation with constant coefficients of order n, we expect to get n independent solutions. Now, in all of the examples that we did last time, the auxiliary equation had n distinct roots. But what happens if that doesn't happen? What happens if we have repeated roots? Now, let's look at an example. Here's our complementary equation. And the first thing we do is we write it in operator notation. Second derivative of y minus 2 times the first derivative of y plus y equals 0. And then we factor out the y. The polynomial in terms of the operator d is what we call phi of d. We get our auxiliary equation from this complementary, from this polynomial in terms of the operator d. We just take the polynomial in terms of d and write it in terms of m instead. So this is the polynomial phi of m. Yeah, I guess that's legible. Okay. And we factor this polynomial to get the roots. And when I look at this polynomial, I recognize something right off the bat. This is m minus 1 quantity squared. And so that yields my solutions. m1 equals 1. And m sub 2 equals 1. I'm not going to get two distinct independent solutions from this. Now I could try this and say, okay, c1 e to the m1x, that's c1 e to the 1x, which equals c1 e to the x, and put a different constant here. C2 e to the m2x, which is C2 e to the 1 times x, which is C2 e to the x. These aren't independent solutions. They're pretty much the same solution. And for those of us who haven't had linear algebra yet, if we have n solutions, the n solutions are independent if we can't write any one of those solutions in terms of, if we can't write any one of those solutions as the sum of constant multiples of the other solutions. And in the case where we have two solutions, they're independent if we can't take, well, they're independent if one solution is not a constant multiple of the other solution. Hey, this solution is a constant multiple of that solution. I'll prove it to you. C2 e to the x equals C2 over C1 times C1 e to the x. We'll call that C3. Constant divided by constant is constant. And see, the C1s just cancel. And C2 e to the x is just C3 times C1 e to the x. We only have one independent solution here. But since we started out with a second order differential equation, we feel like we should have two independent solutions. But how are we going to get two independent solutions when we only have one root, one distinct root to the auxiliary equation? Here's what we do. We'll take this guy as our first solution, C1 e to the x. That's solution 1. Now to get our second independent solution, what we do is we take the first solution and multiply it by x. These two things are independent. One of these is not a constant multiple of the other. And then our general complementary solution is the sum of these two things. Whoops, let's make that a different constant. C2 x e to the x. Now our only concern is, okay, these two things are independent, but is this thing a solution to the complementary equation? We took this thing and multiplied it by x, so is this thing still a solution? And here's what we're going to do. We're going to show that this thing is a solution. Our prospective complementary solution, we're going to show that that's a solution to the original complementary equation. So here's v. We're going to compute the derivative v prime and the derivative v double prime and plug all of these into the original complementary equation and show that we get 0. Okay, derivative of c1 e to the x, that's c1 e to the x. Derivative of c2, whoops, no, wait a minute. This is a product. We're going to have to use the product rule. Most of you didn't have me for Cal 1, so the form of the product rule that you probably learned was first times derivative of the second plus second times derivative of the first. So here's first times derivative of the second, e to the x is its own derivative, plus the second, e to the x, times derivative of the first, there. Now I'll simplify. C1 e to the x plus C2 e to the x plus C2x e to the x. Okay, there's our our first derivative. Now our second derivative, v prime. Compute the derivative of this, it's C1 e to the x. The derivative of this, C2 e to the x. And then we got to compute this derivative where we use the product rule, but we already computed the derivative of this thing up here. We know what it turns out to be. The derivative of this thing is C2 x e to the x, and so forth. C2 x e to the x plus e to the x times 1. Okay. And I'll simplify. V prime is C1 e to the x plus C2 e to the x plus another C2 e to the x. So that's 2 C2 e to the x plus C2x e to the x. Okay, so there's first, second, no, there's V, V prime, V double prime. And here's what we're going to do. Substitute V, V prime, V double prime for Y, Y prime, Y double prime in the equation Y double prime minus 2Y prime plus Y equals 0. Okay, so Y double prime. We're going to substitute V double prime in for that. So we get C1 e to the x plus C2 e to the x plus C2 x e to the x. So that's our V double prime, which equals Y double prime. And then we have minus 2 times Y prime, and we're going to put V prime in for that. C1 e to the x plus C2 e to the x plus C2x e to the x. So this is our minus 2 V double prime, which is minus 2Y prime. And I guess I don't really have enough room to keep writing here, do I? But finally we add Y. So C1 e to the x plus C2 x e to the x. So this is our, this is our V equals Y. And up here, please correct this. I wrote 2V double prime here. It should just be negative 2V prime. Now, let's collect everything and see what we get. And I notice I have c1 e to the x, c1 e to the x, c1 e to the x. So I'm going to factor c1 e to the x out of each term. And here I have 1 c1 e to the x. Here I have minus 2 c1 e to the x. So 1 minus 2. And here I have 1 c1 e to the x. Okay. Now, what else do I have as a common factor? c2 e to the x, 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 c2 e to the x. Okay, so I have a common factor of c2 e to the x. Here's 1 c2 e to the x plus x c2 e to the x. We have minus 2 c2 e to the x and minus 2x e to the x, minus 2x c2 e to the x. And then we have x e to the x. And what happens here? We got 1 minus 2 plus 1, that's 0. And we have 1 minus 2. Oh, did I shoot myself in the foot here? Let me see. I have 1 c2 e to the x plus x c2 e to the x minus 2 c1 e to the x. No. 1 c2 e to the x plus x c2 e to the x minus 2 c2 e to the x minus 2x c2 e to the x. And I have missed something here. Let me make sure I've written it right. Nope, here is my problem. V double prime is c1 e to the x plus 2c2 e to the x plus c2x e to the x. Yep, here's my problem. This is 2c2 e to the x. And so this 1 right here should actually be a 2. Okay. So 2 minus 2 is 0, thank goodness. And over here, x plus x minus 2x is 0. So all of this works out to be 0, especially if we do the math right the first time. Ah. So this thing is the general complementary solution. So taking the first solution and multiplying it by x will give us the second independent solution in the case where we have repeated roots. Now let's illustrate this again with an exercise that's slightly more complicated. So that's y triple prime plus 6y double prime plus 12y prime plus 8y equals 0. This is the complementary equation of some differential equation. And to solve it, the first thing we do is we write it in operator notation. Third derivative of y plus 6 times the second derivative of y plus 12 times the first derivative of y plus, and I haven't written this right, make this 8y, please. 8y. The next step, factor out y. And what this gives us is our polynomial phi of d. To get the auxiliary equation, what we do is we just replace d with the variable m. And we factor that and solve it for m. Now, I don't know about you, but any polynomial of order 3 or greater, I don't have an easy time factoring it. So here's what I do. I take the constant term, and I take each of the whole number factors of this constant term and plug them into the polynomial, hoping that I get 0. And I'll tell you why later on. But let me try this. Plus and minus 1 are factors of 8. So if I plug in 1, I get 1. Plus 6 is 7. Plus 12 is 19. Plus 8 is 27. No, that's certainly not 0. Let's try m equal negative 1. We get negative 1 plus 6 is 5. Minus 12 is negative 7. Plus 8 is 1. Well, that's closer to 0, but it's not 0. Okay, 2 and negative 2 are factors of 8. Since all of my terms here are positive, let me try negative 2. I plug in negative 2 here and I get negative 8. Well, negative 8 here will wipe out that positive 8. And then I plug negative 2 in here, I get 6 times 4 is 24. Minus 24 is 0. Okay, great. If I plug negative 2 into this polynomial, I get 0. Here's my polynomial, phi of m. And what I've just figured out is that phi of negative 2 equals 0. Now, why is that so important? I'll tell you why. If we have a polynomial like phi of m, and we can find a number to plug into this polynomial that makes the polynomial 0, then the variable minus that number is a factor of the polynomial. I'll say that again. The variable m minus this number, the number that makes the polynomial 0, is a factor. Now, when I tidy things up a bit, that means that m plus 2 is a factor. Now, once I have one factor of the polynomial, the others are usually not all that hard to get. So, let me write down my polynomial again. Here's phi of m. See, m cubed plus 6m squared plus 12m plus 8 equals m plus 2 times some other factor. Now we're trying to get a third degree polynomial. So what we're going to have is m plus 2 times a second degree polynomial. So we got something times m squared here. Whatever we have here has to multiply by m to give us m cubed. So what times m gives us m cubed? It's got to be m squared. Also, whatever goes here as the constant term has to multiply 2 to yield 8. Now, what constant times 2 gives us 8? It's got to be 4. So here's the constant 4. The only term we're lacking is the middle term. And to find that, we choose one of these two middle terms. Let's see, we have 2 times m squared here. But over here we have 6 times m squared. 2m squared here, 6m squared here. Whatever goes here has to multiply by m to give us the other 4m squared. So in other words, this thing times m has to give us 4m squared. It's got to be 4m. Now let me just make sure this worked. Let's see. M times 4m is 4m squared, plus 2m squared is 6m squared. Check. Now if we still have our doubts, let's check the first degree term. M times 4 is 4m, and 2 times 4m is 8m. 4m plus 8m is 12m. Check. We nailed it. Now I just have to factor this thing. And you know what? Something hits me right between the eyes here. I look at this and it's a recognizable form. This is a perfect square. And I recognize it as m plus 2 quantity squared. That's what that is. So really, I have m plus 2 times m plus 2 quantity squared is m plus 2 quantity cubed. That's my polynomial. This is my phi of m. And that's got to equal 0. So here's what we get. M sub 1 equals negative 2. M sub 2 equals negative 2. M sub 3 equals negative 2. We have a triple root here. There's only one distinct root, and that's m equal negative 2. But we have a third order differential equation. So we expect to have 3 independent solutions. e to the negative 2x is going to give us one of those, but where are we going to get the other two? Let's see, here's our complementary solution. C1 e to the negative 2x. Now, based on what we did in the previous example, we might say, okay, take this thing and multiply it by x. And if we did that, essentially, we'd be right. Take e to the negative 2x and multiply it by x, and that gives us another independent solution. But we still need a third independent solution, so how are we going to get that? Based on what we've already done, we might say, take this thing right here and multiply it by x. And you know what? That's exactly what we do. So we'll have c sub 3x squared e to the negative 2x. And this is our general complementary solution. Now, I doubt that we would ever have an auxiliary equation that had a quadruple root. But suppose we did. Suppose that m equal negative 2 was a quadruple root. How would we get our general complementary solution? The same exact way. We'd have c1 e to the negative 2x plus c2x e to the negative 2x plus c3x squared e to the negative 2x plus c4x cubed e to the negative 2x. That's exactly what we would get. And this pattern continues if we have 5 repeated roots. We essentially continue the process and so forth. So that's the first thing that can go wrong when we're looking for a complementary solution. But really, it's not a big deal. We've shown how to deal with that. Next time, we'll look at what happens when we have, heavens to Betsy, an auxiliary equation with imaginary or complex roots. It can happen. Now, before I go, I want to say 2 things. One, homework. Homework, page 177, A exercises. Number 1 and number 2. And then the other thing that I want to say is, in the coming days and weeks, please exercise soundness of mind in everything that you do, because I'm looking forward to the time when all of you will be back here in this classroom in person, and I can gaze upon your beautiful faces. And I say that with a smile on my face, but I say that in utmost sincerity also.